Hello, and welcome to Section 1.1 Rates of Change. Let's begin by understanding what we mean by rate of change. Rate of change is simply how one quantity changes compared to another. In daily life, we see this all the time. Your speed shows how quickly your position changes over the time. A business may track how its profits increase or decrease over months. When we analyze these types of changes using math, we are calculating a rate of change. In this section, we'll look at two key types of rate of change: average rate of change and instantaneous rate of change. Let's start with average rate of change. The average rate of change tells us how much something changes over an interval. For example, if we look at this table, we can see car is worth $22,000 when it's new, and it's worth $4,050 after 10 years. So we can calculate how much value it lost per year. Generally, we use this formula, change in value divided by change in time, or y2 minus y1 over x2 minus x1. For the car example, that's 4,050 minus 22,000 divided by 10. That gives us negative $1,795 per year. This means the car lost about $1,795 each year, on average. Now let's talk about instantaneous rate of change. This tells us how fast something is changing at an exact moment. It's like checking your speedometer while driving. It shows how fast you're going right now, not your average over the whole trip. Mathematically, this is represented by the slope of a tangent line, a line that just touches the curve at one point. Let's see this idea with a quick demonstration. On the screen, we have a graph of the function f of x equal 1/2 x squared. Watch what happens as we move the point of contact for the tangent line. When x is negative, the tangent slopes downward. That means the slope or rate of change is negative. As x moves closer to 0, the tangent line becomes less steep. And exactly at x equals 0, the line is flat, the slope is 0. As x increases beyond 0, the tangent begins to tilt upward. Now the slope is positive, and it gets steeper as x increases. This shows how the instantaneous rate of change or slope of the tangent changes depending on the position on the curve. Now let's move on to another real-world example. A balloon is being inflated. At 21 seconds, its volume is 1,436 cubic centimeters. At 30 seconds, the volume is 4,186.7 cubic centimeters. The average rate of change from 21 to 30 seconds is 2,750.7 divided by 9, which gives about 305.6 cubic centimeters per second. Now, to estimate the instantaneous rate of change at exactly 21 seconds, we use 2 points very close together, like 21 and 16.5 seconds. That gives us a rate of about 208 cubic centimeters per second. Let's explore one more interesting example: water depth in containers. When you pour water at a constant rate into a cylindrical container, the depth of water rises steadily. This gives a straight line when you graph depth versus time. That means the rate of change is constant. Now imagine pouring water into a conical vase. At first, the depth rises quickly because the bottom is narrow. As more water fills the wider top, the depth rises more slowly. This creates a curve, not a straight line. So the rate of change is decreasing over time. Let's wrap up with a quick recap. Average rate of change looks at how much something changes over a period of time. Instantaneous rate of change looks at how fast something is changing at a single moment. We saw this in the balloon example, the car value, and even with pouring water into different containers, and we visualized it clearly with our tangent line demonstration. These ideas are the foundation of everything that comes next in calculus. Now, a couple of quick math challenge questions from the textbook. First, if x plus y equals 8 and x times y equals 12, what is 1 over x plus 1 over y? We simplify using the identity. 1 over x plus 1 over y equals x plus y over xy. That gives us 8 over 12, which simplifies to 2/3. Second, if 5 cubed equals g, what is log base 9 of g? 5 cubed is 125, so we're looking for log base 9 of 125. Using the change of base formula and an estimate for log base 3 of 5, we find that the result is approximately 2.196. Thanks for watching, and I'll see you in the next lesson.